Hey guys, welcome back to another episode of the Wikiclick podcast. As always, this is Kyle Hellcamp. Last time we talked a little bit about science, and we found that there are, in fact, some subjects where I will not delve into history. Not that there's anything wrong with history, but man, maybe I'm probably borderline addicted to it. It turns out that the one, subject more addicting is science. So let's follow that thread today, because science is fun. Everyone loves science and discoveries. I'm going to start off with an article called Proxima Centauri b. Now, Proxima Centauri is the star system that is closest to our sun. It's about 4.2 light years away. And I believe there are 3 stars within it. And of those, I think 2 of them are like normie stars and 1 is a red dwarf. But Proxima Centauri b is interesting because it's an exoplanet around the red dwarf of the star Proxima Centauri. So let's read about this exoplanet. And the reason I chose it is because it's orbiting within the red dwarf's habitable zone. Proxima Centauri b is an exoplanet orbiting in the habitable zone of the red dwarf star Proxima Centauri, which is the closest star to the Sun and part of a triple star system. It is located about 4.2 light years from Earth in the constellation Centaurus, making it the closest known exoplanet to the solar system. So, not only is it in the habitable zone, but it's the closest exoplanet. Not in my lifetime, not in my grandkids' lifetime, and not in their grandkids' lifetime, but maybe someday we'll actually reach that. Proxima Centauri b orbits the star at a distance of roughly 0.05 AU, which is astronomical units, with an orbital period. The astronomical unit is the average distance Earth is from the Sun. So 1 AU is the Earth-Sun distance. This is 0.05, so this is 5% that. Keep in mind, red dwarfs are very dim compared to what our sun puts out, so the habitable zone is much closer. Proxima Centauri b orbits the star at a distance of roughly 0.05 AU with an orbital period of approximately 11.2 Earth days and has an estimated mass of at least 1.3 times that of Earth. Its habitability has not been established, though it is unlikely to be habitable since the planet is subject to stellar wind pressures of more than 2,000 times those experienced by Earth from the solar wind. So they think that probably the solar winds from its star stripped the planet of all of its atmosphere. Makes sense. The discovery of the planet was announced in August of 2016 by the European Southern Observatory. The planet was found using radial velocity method, where periodic Doppler shifts of spectral lines of the host star suggest an orbiting object. So that was a lot to take in. Essentially what happens is stars give off light. You've got a star right here, and it's giving off light, sending out these rays. These rays have spectral lines on them. So if you observe them with a spectrometer, you can see these lines. Now, if something is orbiting the star, the thing orbiting the star will pull on it just slightly so that the star wobbles. And as the star is wobbling, because of the object pulling on it, in this case the planet, the spectral lines will shift ever so slightly. So instead of the lines being here, they'll go back and forth and back and forth and back and forth, even though in the middle is where they're supposed to be, because we know what the spectral lines for every element out there are. So that's just an explanation for how it was discovered. Let's see. Its proximity to Earth offers an opportunity for robot exploration of the planet with the Starshot project, or at least in the coming centuries. So I'm going to click on Starshot, because how can you not click on an article relating to potentially future discoveries around other suns, probes, and what have you? Breakthrough Starshot is a research and engineering project by the Breakthrough Initiatives to develop a proof-of-concept fleet of light-sail spacecraft named Starship. to be capable of making the journey to Alpha Centauri star system 4.37 light years away. So it says 4.2 in the last article. This one says 4.37. Once you've traveled the 4, the last little point difference isn't that big of a deal. A flyby mission has been proposed to Proxima Centauri b, an Earth-sized exoplanet in the habitable zone of its host star, Proxima Centauri, an Alpha Centauri system. At a speed of between 15% and 20% the speed of light, it would take roughly between 20 and 30 years to complete the journey, and approximately 4 years for a return message from the starship to Earth. Because they say a light year, that is the distance it takes for light to travel in a year. So you've got the star, and you've got the little probe around it. And it's so far away that if you shot a flashlight, or in this case a radio signal, out toward Earth, that takes 4.2 to 4.37 years to reach Earth. So getting a physical object out there itself is its own bucket of fish. I'm going to scroll down. It's where it's got a list down here. Project Star Breakthrough Starshot has a pretty big article associated with it. So let's go down to the objectives. The Breakthrough Starshot program aims to demonstrate a proof of concept for ultra-fast, light-driven nano spacecraft and lay the foundations for a first launch to Alpha Centauri within the next generation. That's pretty ambitious. Secondary goals are solar system exploration and detection of Earth-crossing asteroids. Oh, and that's it. The spacecraft would make a flyby of and possibly photograph any Earth-like worlds that might exist in the system. In 2016, the European Southern Observatory announced the detection of a planet orbiting the third star in the Alpha Centauri system, Proxima Centauri. The planet, called Proxima Centauri b, is orbiting within the habitable zone of its star, and it could be a potential target for one of the projects of the Breakthrough Initiatives. In January of 2017, Breakthrough Initiatives, the European Southern Observatory, entered a collaboration to search for habitable planets in the nearby star system, Alpha Centauri. The agreement involves Breakthrough Initiatives provided funding for an upgrade to the VISIR, which is the VLT imager and spectrometer for mid-infrared, and VLT stands for Very Large Telescope. Astronomers are not known for their originality, so you've got things like the VLT, which is a Very Large Telescope, and I think there's an ELT, which is Extremely Large Telescope. Let's go down to technical challenges. Light propulsion requires enormous power. A laser with a gigawatt of power, approximately the output of a large nuclear plant, would provide only a few newtons of thrust. A spaceship will compensate for the low thrust by having a mass of only a few grams. The camera, computer, communications laser, a plutonium power source, and the solar sail must be miniaturized to fit within a mass limit. All components must be engineered to endure extreme acceleration, cold, vacuum, and protons. The spacecraft will have to survive collisions with space dust. Starshot expects each square centimeter of frontal cross-section to collide at high speed with about 1,000 particles of a size of at least 0.1 micrometers. So very, very, very fine dust. Focusing a set of lasers totaling 100 gigawatts onto the solar sail will be difficult due to atmospheric turbulence. So they're thinking of launching this thing into space, pointing a laser up from the ground, and shooting the laser directly at the sail. According to The Economist, at least a dozen off-the-shelf technologies will need to improve by orders of magnitude, and that does make sense. Not just the laser capabilities, aiming the lasers, but probably battery technology. You're going to have to scale down the camera. You're going to have to make sure that the laser is focused back on us. Material science is going to have to improve in order to protect the little space components from all these little bits of dust. Otherwise, when it gets there, the photos aren't going to work. You can't take a picture with a camera that's been bombarded with all these little pieces of dust. Let's see. So I'm going to scroll down. There's also see also where it has a list of other kind of related. I'm going to click on 2069 Alpha Centauri mission because that seems, you talk about ambitious. NASA introduced in December 2017 a mission concept to launch an interstellar probe by the year 2069 to search for biosignatures on planets around the stars in the Alpha Centauri system. The mission concept is not fully funded, unnamed, and the technology to get there does not exist. So, pretty ambitious. A preliminary mission concept suggests using solar sails propelled by high-energy lasers to increase propulsion. The proposed launch would be on the 100th anniversary of the Apollo 11 mission. And that's the entirety of the article. I'm going to click on biosignatures because I know for a fact that there are certain things that they look for in atmospheres around exoplanets and what have you in order to detect whether or not life doesn't necessarily exist there, but is likely. I know that they say that if you see oxygen in the atmosphere, free form oxygen, it's a good indicator that there's probably some sort of biological process occurring. And the reason is because oxygen is a very reactive gas and it tends to bond with a lot of other elements. So you'll have oxygen bonding and creating rust, for example. You've got that on Mars. You've got water, which is pretty common. So let's look at biosignature. A biosignature is any substance, such as an element, isotope, molecule, or phenomena, that provides scientific evidence of past or present life. Measurable attributes of life include its complex physical and chemical structures and also its utilization of free energy and the production of biomass and wastes. Due to, well, when it says utilization of free energy, I think what it means is conversion of non-living energy into living energy. Due to its unique characteristics, a biosignature can be interpreted as having been produced by living organisms. However, it is important that they not be considered definitive because there is no way of knowing in advance which ones are universal to life and which ones are unique to the peculiar circumstances of life on Earth. So regarding that oxygen thing, if we spend all of our time searching for oxygen in the atmosphere and we find absolutely none, initially you might think, oh, well, that concludes it. That's obvious that there's no life out there. But how do we know that other life needs oxygen? For instance, plants need quite the opposite. They got carbon dioxide is what they need. You might run into a situation where the life forms don't use those gases or maybe even any gases at all. We don't know whether or not the respiratory system will require the exchange of gases. I'd say it's probably likely, but we don't know. Nonetheless, life forms are known to shed unique chemicals, including DNA, into the environment as evidence of their presence in a particular location. So that in itself seems like a bit presumptuous on Wikipedia's part, because it says shed unique chemicals. I mean, how are we so certain that there aren't crystalline formations out there, like like a zircon crystal kind of creature? We know zircon's a fairly common crystal. It's a silicate located here on Earth, but okay, we'll give them the benefit of the doubt. They're the ones that are editable. You can't edit me as easily, I guess. In geomicrobiology, so they're going to talk about geomicrobiology, which I know what words mean, and I sort of do, even though I can't pronounce them half the time. Geomicrobiology is the study of microbiology is related to geology, so probably tiny microbial fossils in the geological record. The ancient record on Earth provides an opportunity to see what geochemical signatures are produced by microbial life and how these signatures are preserved over geological time. Some related disciplines such as geochemistry, geobiology, and geomicrobiology often use biosignatures to determine if living organisms are or were present in the sample. These possible biosignatures include microfossils and stromatolites, molecular structures, and isotopic compositions of carbon, nitrogen, and hydrogen organic matter. I'm going to click on stromatolites because I don't know what that is and I don't know how to pronounce it, but maybe Wikipedia can kind of lead me in the right direction. Let's see. Stromatolites. I'm going to say stromatolite. Stromatolites, or stromatoliths, are layered mounds, columns, and sheet-like sedimentary rocks that were originally formed by the growth of layer upon layer of cyanobacteria, a single-celled photosynthesizing microbe. Fossilized stromatolites, some of which may date from 3.7 billion years ago, provide records of ancient life on Earth. Lichen stromatolites are a proposed mechanism of formation of some kinds of layered rock structure that are formed above water, where rock meets air, by repeated colonization of the rock by endolithic lichens. So it sounds like these lichens built up on top of themselves, lived, died, became rock, lived, died, became rock, and they were just crawling all over their ancestors' dead remains. Let's look up 3.7 billion years ago. Holy cow. There's a once again, I delve back into the world of history, but there's a life timeline off to the right here. And at the very top, you had multicellular life 1.5 billion years ago. Primates barely make the top. I'm going to... Photosynthesis is about 3.5 billion. I'm going to click on earliest water. Let's find out where all this water on Earth came from. Because we got water on Earth. We got a lot of water on Earth. And I've heard different theories. I think the cometary bombardment theory is probably the most widely accepted, but let's find out if Wikipedia agrees. The origin of water on Earth, or the reason that there's clearly more liquid water on Earth than on other rocky planets of the solar system, is not completely understood. There exist numerous more or less mutually compatible hypotheses as to how water may have accumulated on Earth's surface over the past 4.5 billion years in sufficient quantities to form oceans. Extraplanetary sources: comets, trans-Neptunian objects, or water-rich meteoroids from the outer reaches of the asteroid belt colliding with Earth may have brought water to the world's oceans. Asteroids may have been primarily responsible based on several studies, including measurements of the ratio of the hydrogen isotopes deuterium and protium, since similar percentage impurities as in carbon-rich chondrites were found in oceanic water, whereas previous measurements of the isotopes' concentrations in comets and trans-Neptunian objects correspond only slightly to water on Earth. So what they're doing is they're measuring the different isotopes within these sources and comparing them to one another. That was a long-winded way to say that. Sometimes Wikipedia can get very, very wordy with what it needs to say, and that's not a bad thing, but for the sake of brevity and the sake of a podcast, sometimes you'll run into these long run-on sentences where you can just summarize it in a quick statement. Large enough planetesimals were heated by the decay of aluminum isotope. Let's scroll down a little bit. Actually, here's that timeline. Let's go back to... Let's look up the evolution of photosynthesis. Because I know about photosynthesis. Plants love it. And because I eat plants and I eat things that eat plants, I love it too. Where did this come from? Let me take a sip here. The evolution of photosynthesis refers to the origin and subsequent evolution of photosynthesis, the process by which light energy synthesizes sugars from carbon dioxide, releasing oxygen as a waste product, which is pretty good for us. The first photosynthetic organisms probably evolved early in the evolutionary history of life, and most likely used reducing agents such as hydrogen or electrons, rather than water. There are three major metabolic pathways by which photosynthesis is carried out: C3 photosynthesis, C4 photosynthesis, and CAM photosynthesis. C3 is the oldest and most common form. C3 is a plant that uses the Calvin cycle for the initial steps and incorporates CO2 into organic material. C4 is a plant that prefaces the Calvin cycle. So they're just going to give you different examples. Let's scroll past that. Let's see. The biochemical capacity to use water as the source for electrons in photosynthesis evolved in a common ancestor of extant cyanobacteria. The geological record indicates that this transforming event took place early in Earth's history, at least 2.45 billion to 2.32 billion years ago, and it is speculated much earlier. Available evidence from the geobiological studies of archean and sedimentary rocks indicates that life existed 3.5 million years ago, or 3.5 billion, but the question of when oxygenic photosynthesis evolved is still unanswered. A clear paleontological window on cyanobacterial evolution opened about 2 billion years ago, revealing an already diverse biota of blue-greens. Cyanobacteria remain principal blue-greens. Blech. This is very wordy. Let's click on the oxygen crisis, because I know we kind of went from water, we skipped over single-celled life, and we're at photosynthesis. So we know that oxygen eventually became abundant enough to appear in the atmosphere. That is, it no longer was bonding with things like iron in the soil, or it was no longer creating other molecules. So the Great Oxygenation Event. The Great Oxygenation Event. The beginning of which is commonly known in scientific media as the Great Oxidation Event. Okay, so that's how I've always pronounced it, or heard it said. Also called the oxygen catastrophe, was the biological induced appearance of dioxygen, which is O2, which, by the way, is how it's present in the atmosphere for the most part. Oxygen, being very, very reactive, will bond with itself. So you have two oxygen atoms bonded together. And actually, a lot of the gases do that. Nitrogen tends to do that. Hydrogen does as well. I believe that there are 7 gases that you'll find them in a diametric molecule with themselves pretty frequently. Now, I think ozone is O3, which is 3 of those bonded together. But anyway, was a biologically induced appearance of dioxygen in Earth's atmosphere. Geological, isotopic, and chemical evidence suggests that this major environmental change happened around 2.45 billion years ago during the Siderean period. At the beginning of the Proterozoic era, eon. Some of these words, man. The causes of the event remain unclear. As of 2016, the geochemical and biomarker evidence for the development of oxygenetic photosynthesis has been mostly inconclusive. So let's look up the events, the timing. The most widely accepted chronology of the Great Oxygenation Event suggests that free oxygen was first produced by prokaryotic and then later eukaryotic organisms that carried out photosynthesis more efficiently, producing oxygen as a waste product. So they ramped up productions, kind of like what we see today. The more energy intensive your system, the more waste product. And so because a more efficient photosynthesis was created, was eventually evolved, the waste products increased. The first oxygen-producing organisms arose long before the GOE, perhaps as early as 3.4 billion years ago. Initially, the oxygen they produced would have been quickly been removed from the atmosphere by chemical weathering of reducing minerals, most notably iron. So essentially what I was saying with it bonding. This mass rusting led to the deposits of iron 3 oxide in the form of banded iron formations, such as the sediments in Minnesota and Pilbara, Western Australia. The saturations of these mineral sinks and the resulting persistence of oxygen in the atmosphere led within 50 million years to the start of the Great Oxidation Event. Oxygen could have been, they have it initialized as GOE. Oxygen could have been accumulated very rapidly. At today's rates of photosynthesis, modern atmospheric O2 levels could be produced in only 2,000 years. That's pretty fascinating. And keep in mind, there were no, I guess you wouldn't have any animals back then, really anything feeding off of, so probably a lot quicker. That's 2,000 years to change the atmosphere that quickly. Another hypothesis is that oxygen producers did not evolve until a few million years before the major rise in atmospheric oxygen concentration. This is based on a particular interpretation of a supposed oxygen indicator used in previous studies. In either case, oxygen did eventually accumulate in the atmosphere with two major consequences. Firstly, it oxidized atmospheric methane to carbon dioxide. So it took a strong greenhouse gas and turned it into a weaker one. And water. This decreased the greenhouse effect on the Earth's atmosphere, causing planetary cooling and triggering the Huronian glaciation, starting around 2.4 billion years ago. This lasted 300 to 400 million years and may have been the longest ever Snowball Earth episode. Secondly, the increased oxygen concentrations provided a new opportunity for biological diversification, as well as tremendous changes in the nature of chemical interactions between rocks, sand, clay, and other geological substrates in the Earth's air, oceans, and other surface waters. Despite the natural recycling of organic matter, life had remained energetically limited until the widespread availability of oxygen. This breakthrough in metabolic evolution greatly increased the free energy available to living organisms, with global environmental impacts. For example, mitochondria evolved after the GOE, giving organisms the energy to exploit new, more complex morphologies, interacting to increasingly complex ecosystems. So that's cool. It says that mitochondria evolving allowed for more complex morphologies. I wonder if that means that if mitochondria had never evolved, if it would just be a more simplistic kind of life here on Earth today, if we would just be a bunch of green sludge, just unable to evolve into anything more impressive. Let's click on Snowball Earth, because I've heard about these kind of phenomena throughout history where the Earth will completely kind of blanket itself in ice. And when I say blanket itself in ice, I'm not talking about like an ice age. An ice age is just a cool day compared to what Snowball Earth episode is. Supposedly, Snowball Earth is like where the entire planet ices over. I mean, you could be in Florida, you could be on the equator, and you're still contending with frozen oceans. The Snowball Earth hypothesis proposes that Earth's surface became entirely or nearly entirely frozen at least once, sometime earlier than 650 million years ago. Proponents of the hypothesis argue that it best explains sedimentary deposits generally regarded as of glaciation origin at tropical paleolatitudes. So paleoaltitudes. There we go. Paleolatitudes are basically, we know how the continents shift around. And we know that Antarctica, for instance, used to be near the tropics. Well, it was in the tropics during this time period, and yet during this time period, when we dig down to the geological record, we're finding sediments associated with glaciation. So we're looking at things, we're looking at the sediments in the soil, comparing it to the time period where we know where it was, thinking to ourselves, wait a second, how come there are glaciation sediments here when it was in the tropics? Now that would either mean that this piece of land somehow magically teleported itself to the rest of the continental shelf, which we know is able to move slowly, or it was just that cold. Opponents of the hypothesis contest the implications of the geological evidence for global glaciation and the geophysical feasibility of an ice or slush-covered ocean, and emphasize the difficulty of escaping an all-frozen condition. Also a fair criticism, because if you're completely frozen over, we know we're taught in school that ice reflects a lot of sunlight. So if you got a big ball of ice right here, it's reflecting sunlight. It's not getting warmer because there's nothing there to absorb the sunlight. All that light is hitting and bouncing back off into space. And then it's just growing colder and colder. And then the ice in the ocean is growing thicker and thicker and thicker. And how do you escape from it? There are some hypotheses here, and we'll get into those here in a little bit. A number of unanswered questions remain, including whether the Earth was a full snowball or a slush ball with a thin equatorial band of open or seasonally open water. The Snowball Earth episodes are proposed to have occurred before the sudden radiation of multicellular bioforms, known as the Cambrian explosion. The most recent Snowball episode may have triggered the evolution of multicellularity. Now that's interesting. Another, much earlier and longer Snowball episode, the Himalayan glaciation, which would have occurred 2.4 to 2.1 billion years ago, may have been triggered by the first appearance of oxygen. This is the GOE we were talking about. Let's look up... man, this is a big article. For those of you that are interested in this, and this is an interesting piece, there are quite a bit. History, we've got the evidence for glaciation mounts and global glaciation where it was proposed. The evidence, which paleomagnetism, low latitude glacial deposits, open water deposits, carbon isotope, banded iron formation mechanisms. Let's look up the mechanisms, because this is kind of where the continental distribution during the frozen period. So this is kind of the mechanism's kind of the start, middle, finish of the glaciation. The initiation of a snowball Earth event would involve some initial cooling mechanism, which would result in an increase in Earth's coverage of snow and ice. The increase in Earth's coverage of snow and ice would in turn increase Earth's albedo, which would result in positive feedback for cooling. Albedo, by the way, is a measurement of a planet's reflectability in space. So if you have, like, let's say a very, very, very dark planet, its albedo is going to be much, much less, because it's not reflecting anything. It's absorbing all of it. So you have a black planet and a white planet. And y'all ever noticed that black planets be like this, but white planets be like this? No. So let's say you have a black planet. It's going to absorb all the radiation that you send to it, because black absorbs all light. My eye patch, for example, is absorbing way more light than my skin. My skin is reflecting more light off. So the albedo right here is much less reflective. It's got less reflectability, so very low albedo. Whereas my skin has a high albedo, baby. Yeah. If enough snow and ice accumulates, runaway cooling would result. This positive feedback is facilitated by an equatorial continental distribution, which would allow ice to accumulate in the regions closer to the equator, where solar radiation is most direct. So what they're saying is, if you have a lot of continents in the equatorial region, equatorial regions are land regions, rather, will accumulate ice way easier than open ocean, because ocean you have currents to contend with, and the freezing point for the ocean is much cooler than it is on the surface of the on land. Plus, you can actually have it accumulate over large periods of time. So essentially what it's saying is, this is kind of like the perfect storm of all, something's cooling it. There's a lot of land around the equator. It's accumulating ice. This ice is reflecting more sunlight. The planet's getting colder. Many possible triggering mechanisms could account for the beginning of a snowball Earth, such as the eruption of a supervolcano, a reduction in the atmospheric concentration of greenhouse gases such as methane or carbon dioxide, changes in solar energy output, or perturbations of Earth's orbit. Regardless of the trigger, initial cooling results in an increase in the area of Earth's surface covered by snow and ice, and the additional ice and snow reflects more solar energy back into space, further cooling Earth. And so, basically what I was saying. This positive feedback loop could eventually produce a frozen equator as cold as modern Antarctica. It's also fascinating to think about that if this happened within our past, if this is a valid theory, that excuse me, that the habitability of Earth would have changed dramatically for what we consider habitable, rather, over periods of time. Applying that to exoplanets, maybe we're studying one now that it's way too cold, but here in a few million years will be much warmer. Global warming associated with large accumulations of carbon dioxide in the atmosphere over millions of years, emitted primarily by volcanic activity, is the proposed trigger for melting a snowball Earth. Due to positive feedback for melting, the eventual melting of snow and ice covering most of Earth's surface would require as little as a millennium. That is impressive. It always amazes me how quickly these large-scale global changes can occur. 2,000 years to completely fill the Earth's atmosphere with oxygen. Well, not completely, but to make it that present. 1,000 years to go from a completely ice-covered planet to one where it's melted away. Continental distribution. A tropical distribution of the continents is, perhaps counterintuitively, necessary to allow the initiation of a snowball Earth. Firstly, the tropical continents are more reflective of the open ocean, and so absorb less of the sun's heat. Most of absorption of solar energy on Earth today occurs in tropical oceans. Further, tropical continents are subject to more rainfall, which leads to increased river discharge and erosion. When exposed to air, silicate rocks undergo weathering reactions which remove carbon dioxide from the atmosphere. Now that I did not know. That's pretty fascinating. These reactions proceed in the general form. Rock-forming mineral plus CO2 plus 2O turns into cations, bicarbonate, and silicon dioxide. The released calcium cations with the dissolved, so it gives an example right here with calcium silicate trioxide. This transfer of carbon. I'm going to scroll down a little bit. Additional factors that may have contributed to the onset of the Neoproterozoic snowball include introduction of atmospheric free oxygen, which may have reached sufficient quantities to react with methane in the atmosphere, oxidizing it to carbon dioxide, which is a much weaker greenhouse gas, and a younger, thus fainter sun, which would have emitted 6% less radiation in the Neoproterozoic. Now that's interesting. I did not know that. I did know that the Earth or the sun emitted less light over time, but that it was that noticeable of a difference. Normally, as Earth gets colder due to natural climatic fluctuations and changes in incoming solar radiation, the cooling slows these weathering reactions. As a result, less carbon dioxide is removed from the atmosphere, and Earth warms as this greenhouse gas accumulates. This negative feedback process limits the magnitude of cooling. During the Cryogenian period, however, Earth's continents were all at tropical latitudes, which made this moderating process less effective, as high weathering rates continued on land even as Earth cooled. This led to advance. Once ice advanced to within 30 degrees of the equator, positive feedback could ensue. Increased reflectiveness, albedo, of the land ice led to further cooling and formation of more ice until the whole Earth was ice-covered. Polar continents, due to low rates of evaporation, are too dry to allow substantial carbon deposition. So it's kind of interesting because most people would probably think that polar regions, land in polar regions would lead to a more icy Earth, but it's quite the opposite. In January of 2016, Jernon et al. Proposed a shallow hypothesis involving the breakup of the supercontinent Rodinia, linking the eruption and rapid alteration of highly low-class sites along shallow ridges to the massive increase in alkalinity in an ocean with thick ice cover. Jernin et al. Demonstrated that the increase in alkalinity over the glaciation is sufficient to explain the thickness of cap carbonates formed by the alteration. So, pretty wordy. He's essentially saying that whenever the supercontinent Rodinia broke up, the events that occurred thereof led to a snowball Earth. During the frozen period, global temperature fell so low that the equator was as cold as modern-day Antarctica. This low temperature was maintained by the high albedo of the ice sheets, which reflected most incoming solar energy into space. A lack of heat-retaining clouds caused by water vapor freezing out of the atmosphere amplified this effect. So clouds, which would kind of help hold heat to the surface, were not there. They had frozen. The vapor had frozen, fallen to Earth, and settled on the ground. This is the era before clouds. That's interesting. The carbon dioxide levels necessary to unfreeze Earth have been estimated as being 350 times what they are today, about 13% of the atmosphere. Since the Earth was almost completely covered with ice, carbon dioxide could not be withdrawn from the atmosphere by release of alkaline metal ions, weathering out siliceous rocks. Oh, there's the phone. Sorry about that. Someone will get that. Over 4 to 30 million years, enough CO2 and methane, mainly emitted by volcanoes, but also produced by microbes converting organic carbon trapped under the ice into gas, would accumulate to finally cause enough greenhouse effect to make surface ice melt in the tropics until a band of permanently ice-free land and water developed. This would be darker than the ice, and thus absorb more energy from the sun, initiating a positive feedback. Destabilization of substantial deposits of methane rates locked at on the continents, the melting of glaciers would release massive amounts of glacial deposit, which would erode and weather. The resulting sediment applied to the ocean would be high in nutrients, such as phosphorus, which combined with the abundance of CO2 which would trigger a cyanobacteria population explosion, which would cause a relatively rapid reoxygenation of the atmosphere, which may have contributed to the rise of the Ediacaran biota and the subsequent Cambrian explosion, a higher oxygen concentration allowing large multicellular life forms to develop. Although the positive feedback loop would melt the ice in geologically short order, perhaps less than 1,000 years, replenishment of atmospheric oxygen and depletion of the CO2 levels would take another millennia. So 2,000. That's still pretty quick, all things considered. It is possible that carbon dioxide fell enough for Earth to freeze again. This cycle may have repeated until the continents had drifted to more polar latitudes. That's pretty cool to think that the position of the landmasses, I mean, it's obvious that the position of the landmasses does make that market of a difference, but it's also really fascinating to think that it's required that they might, it might be required that they have to be in more polar regions to sustain a less icy Earth. The slush ball Earth hypothesis. While the presence of glaciers is not disputed, the idea that the entire planet was covered in ice is more contentious, leading some scientists to posit a slush ball Earth, in which a band of ice-free or ice-thin waters remain around the equator, allowing for a continued hydrologic cycle. Essentially allowing the water cycle to continue where it wouldn't be completely frozen out. There would be clouds. This hypothesis appeals to scientists who observe certain features of the sedimentary record that can only be formed under open water or rapidly moving ice, which would require somewhere for ice-free to move to. Recent research observed geochemical cyclicity in clastic rocks, showing that the snowball periods were punctuated by warm spells, similar to ice age cycles in recent Earth history. Attempts to construct computer models of snowball Earth have also struggled to accommodate global ice cover without fundamental changes in the laws and constants which govern the planet. Less extreme snowball Earth hypothesis involves continually evolving continental configurations and changes in ocean circulation. Synthesized evidence has produced models indicating a slush ball Earth, where the stratigraphic record does not permit postulating complete global glaciations. Kirschvink's original hypothesis had recognized that warm tropical puddles would be expected to exist in a snowball Earth. The snowball Earth hypothesis does not explain the alteration of glacial and interglacial events, nor the oscillation of glacial sheets and margins. Okay, so you got some contentions here. Let's see. Let's look up. I'm scrolling down. I scroll down to effect on early evolution, and the first blue article is the Neoproterozoic. Neoproterozoic. Let's click on the Neoproterozoic. I'm going to take a sip as I do. The Neoproterozoic era is the unit of geological time from 1 billion to 541 million years ago. It is the era of the Precambrian supereon and the Proterozoic eon. It is subdivided into the Tonian, Cryogenian, and Ediacaran periods. It is preceded by the Mesoproterozoic era, succeeded by the Paleozoic. The most severe glaciation known in the geological record occurred during the Cryogenian, which makes sense, cryo, when ice sheets reached the equator and formed a possible snowball Earth. The earliest fossils of multicellular life are found in the Ediacaran, including the Ediacarians, which were the earliest animals. Okay, so I can't not click on because it says the Ediacarans is a link that I can click on. I can't not find the earliest animal. The Ediacaran biota consisted of enigmatic tubular and frond-shaped, mostly sessile organisms that lived during the Ediacaran period, which was around 635 to 542 million years ago. Trace fossils of these organisms have been found worldwide and represent the earliest known complex multicellular organisms. The Ediacaran biota may have radiated in a proposed event called the Avalon Explosion 575 million years ago, after the Earth had thawed from the Cryogenian period's extensive glaciation. The biota disappeared with the rapid increase in biodiversity known as the Cambrian explosion. So I'm guessing what happened was there was an explosion of life. These life forms thrived, and then another kind of explosion in biodiversity. And the second explosion in biodiversity produced organisms that were much more suited to the environment, causing them to outcompete with the first. You know, life is a self-correcting cycle, it seems. Most of the current existing body plans of animals first appeared in the fossil record in the Cambrian, rather than the Ediacaran. For macroorganisms, the Cambrian biota appears to have completely replaced the organisms that dominated the Ediacaran fossil record, although relationships are still a matter of debate. So that I guess they don't know whether or not they outcompeted them directly. They don't know how appeared and how these newer life forms interacted with the older. The organisms of the Ediacaran period first appeared around 600 million years ago and flourished until the cusp of the Cambrian 400 or 542 million years ago, when the characteristic communities of fossils vanished. The earliest reasonable diverse Ediacaran community was discovered in 1995 in Sonora, Mexico, and is approximately 600 million years in age. Let's see. Scrolling down a little bit. Determining where Ediacaran organisms fit in the tree of life has proven challenging. It is not even established that they were animals, with suggestions that they were lichens, algae, protists, known as foraminiferae, fungi, or microbial colonies, or hypothetical intermediates between plants and animals. Now that would be fascinating. And I guess would kind of make sense if you're outcompeted and, if you're a jack of all trades, you're the master of none. So you're going to be overcome by the animals that are masters in this niche and overcome by the plants that are masters in this niche. The morphology and habit of some taxa suggest relationships. So I guess let's look up, I'm going to scroll down. Let's look up the morphology of these animals because, Yeah, let's look up the morphology. I want to see what these weirdos looked like. And I will describe these in lurid detail. The Ediacaran biota exhibited a vast range of morphological characteristics. Size ranged from millimeters to meters, complexity from blob-like to intricate, rigidity from sturdy and resistant to jelly-soft. Almost all forms of symmetry were present. These organisms differed from earlier fossils by displaying an organized, differentiated multicellular construction in centimeter-plus sizes. Okay, so these guys had specialized cells, just like in your human body. You've got skin cells, and you got teeth cells, and tongue cells, and eyeball cells, and heart cells, liver cells. These guys had similar special functioning cells. And I'm looking at some of these fossils, and you've got this weird, the earliest discovered potential embryo preserved within the term. A lot of these looked kind of like what you would expect ancient life forms living in the ocean to look like. Kind of had a region that you can sort of identify as a head, and then a bunch of is going down its tail. Some of these look tube-like, some of these look circular. So in the morphology, it's talking about embryos, how potentially these are where embryos are created. You've got circular fossils, which are labeled as discs. Bags, which are fossils that resemble mud-filled bags. That's romantic. Toroids. So you got a bunch of different ones. Let's I'm going to scroll up a little bit because this gets into some very heady, wordy details, and I'm going to click on the. Let's see. Yeah, I'm going to click on Tree of Life. The Tree of Life is a widespread. Oh well, this is real. I was clicking on Tree of Life, thinking I was going to get to the one relating to biology, where you see the way that things related to one another, the ancestors of one branching off of into descendants, etc. But this one actually took me to the Tree of Myth. So I'm going to read it. I think that's a little bit of an oversight on Wikipedia's part. I think they meant to have that link to the scientific one. But you know what? Forget it. Let's go to about the myth. Tree of Life is a widespread myth or archetype in the world's mythologies related to the concept of a sacred tree more generally, and hence in religious and philosophical tradition. The expression Tree of Life was used as a metaphor for the phylogenetic tree of common descent in an evolutionary sense in a famous passage by Charles Darwin. The Tree of Knowledge, connected to heaven and the underworld, and the Tree of Life, connecting all forms of creation, are both forms of the world tree or cosmic tree, and are portrayed in various religions and philosophies as the same tree. I do know that there are trees portrayed in a lot of myths. So let's click on World Tree. World Tree hip hop. The world tree is a motif presented in several religions and mythologies, particularly Indo-European religions. And I think it would be fascinating to take all these common myths throughout these faiths and essentially create a tree of life of these myths. We sort of do. We know that, for instance, Islam and Christianity are both Abrahamic faiths, and they're monotheistic, and they came from philosophies and Middle East, ancient times. And we know that these eventually go back far enough. You get animism, and you get tribal spiritualism, etc. I think it would be cool to see a way more specific one where you're able to trace back the okay, this myth has a flood and a tree, so let's take all of those and see if you can kind of compile a way, kind of a list of the way that these changed over time. The world tree is represented as a colossal tree which supports the heavens, thereby connecting the terrestrial world and through its roots, the underworld. It may also be strongly connected to the motif of the Tree of Life, but it is the source of wisdom of the ages. Huh. I'm going to click on the wisdom of the ages, and this is taking me to uh, Yggdrasil, which is an immense mythical tree that connects worlds in Norse mythology or cosmology, and that's the one that uses the Norse tree. They have the most famous tree. Yggdrasil is attested in the Poetic Edda, compiled in the 13th century from earlier traditional sources, and the Prose Edda, written in the 13th century by Snorri Sturluson. In both sources, Yggdrasil is an immense tree that is the center of the cosmos and considered very holy. The gods go to Yggdrasil daily to assemble at their things, or their governing assemblies. The branches of Yggdrasil extend far into the heavens, and the tree is supported by 3 roots that extend far away into other locations. One to the well Aururabrunur in the heavens, spring Hvergelmur, and the other to the well Mimisbrunur. Creatures live within Yggdrasil, including the dragon Níðhåggr, and the eagle, and the stags Dan, Dvalin. Let's click on Níðhåggr, the dragon. I want to see what a Norse dragon looks like. In Norse mythology, Níðhåggr, often anglicized to Níðhågg, which is exactly how I'm going to pronounce that, is a dragon/serpent who gnaws at a root of the world tree, Yggdrasil. In historical Viking society, Níðhågg was a term for social stigma, implying the loss of honor and the status of a villain. Thus, its name might refer to its role as a horrific monster, or in its action of chewing the corpses of the inhabitants of Strand, those guilty of murder, adultery, and oath-breaking, which Norse society considered amongst the worst possible crimes. So I guess, like, on my honor, if you broke that honor, then it was considered one of the worst crimes. In standardized Old Norse orthography, the name is spelled Níðhåggr, but the letter Q, it's like a Q. Well, let's not talk about that. Because this is supposedly an etymology, but for the, I guess, the way it's written, man, why couldn't those Norse have had normal names? Well, regardless, I'm looking at the time right now, and I think it's time for me to get this Norsic language. And let's talk about what we learned here today. We started with Proxima Centauri b, which is a exoplanet, the closest one to our planet. That's about 4.2 light years away, and it's orbiting the red dwarf, the dwarf star, in the Alpha Centauri system. And it might not be habitable, even though it's in the habitable zone, because it might have been subject to a lot of solar winds to strip its atmosphere. We looked at Breakthrough Starshot, which is a proposed concept to send little tiny nano probes to the star system. And who knows, maybe soon. We looked up its objectives, and it wanted to kind of inspect these planets and the stars out there. We had a C also, which was the 2069 Alpha. And this was a very short article that says that this is a proposed mission that wants to send a probe in the year 2069 to Alpha Centauri, but doesn't have any of the technology really available to it yet. So who can argue with that? Biosignature, which is essentially a signature that you find. It's like indirect proof of life, essentially. Or I guess you could say direct proof of life. No, I guess direct proof of life would be looking and saying, hey, look over there, there's life. This would be an indirect proof. And atmospheric composition, fossils. You can't argue that life existed if you see fossils, but we looked up the stromatolite, which is one of the earliest kind of forms of life here on Earth. And it's these are kind of layered structures formed by single cellular organisms building up on top of themselves over time. We looked up the origin of water on Earth, and this was kind of a wordy one, but it's essentially the current hypothesis is a cometary bombardment hypothesis, which says that because comets have, they're about 10 miles across, most of them ice, water ice. imagine a sphere of 10 miles in one direction crashing into Earth, what that would do to the sea levels. It wouldn't take many of those. We looked up the evolution of photosynthesis, and that was also a wordy kind of talking about how it evolved. There were 3 different types, C3, C4, and CAM photosynthesis, but eventually the latter ones produced enough oxygen that an event which filled the atmosphere with enough oxygen that it would there was no longer any other elements for it to bond to. So it filled the atmosphere and kind of poisoned everything. In addition to doing that, because things couldn't, breathe in oxygen, this cooled the planet down so much so that we have a snowball Earth, which is where it's cold enough that even around the equator, ice forms. This is kind of a point of contention. Some people think that it's a full-on ice ball. Others think that it's a slush ball, where there was a thin band of melted area around the equator. I mean, I'm not a professional one way or the other. It does make sense that it would be a slush ball, though. From there, we went to... we kind of looked up and saw that more complex organisms formed after it. We looked up the Neoproterozoic, which is during this time period, where you have the essentially time period predating the Cambrian, the Precambrian. Animals, which were the Ediacaran biota, which they kind of look like what you would expect when you associate ancient fossils, a bunch of things squirming on the ocean floor. They kind of look like that. They definitely don't look like they would be suited to current life, or don't look like they would be able to compete in the current world. But they're cool looking, and they got the job done. They had specialized cells evolve, and we carried that torch. From there, we looked up the Tree of Life, which was supposed to probably be the biological Tree of Life, but we got instead to the mythological archetype of the Tree of Life. And that's fine, because from there we kind of read a little bit about that. We learned a lot of religions have that. The World Tree from the Tree of Life. The tree that is the thing that supports the heavens, grows out of the earth, and its roots travel into the underworld. And that, again, this motif is apparent in a lot of different faiths. From there, one of which is which is a Norse kind of concept, and appears in the Eddas. From there, we looked up Níðhåggr, or Níðhåggr, which was the dragon that chews on the roots of the ancient Tree of Life. So we have it, Proxima Centauri B to Níðhåggr. I hope everyone has enjoyed this episode of Wikiclick podcast, and thank you all for watching. Until next time, bye.